Hello again, and welcome back to XR101. In a previous video we looked at whether VR needed to exist, and we concluded that it does, sometimes, and that this depends on the task or the problem that VR is a potential solution for, what alternative solutions are available, and who the stakeholders are. This video takes things a step further, and presumes that the evidence has already told us that VR is indeed the right solution for our problem. But virtual reality is clearly not a single solution. So the question we now have is, how should VR be deployed to best solve the problem? Well, first things first, what are our options here? Well, a good place to start is at the broadest or upper levels of virtual reality classification, then move into the finer details later. A good example of a broad classifier would be VR platform. Should the solution be mobile VR using a smartphone, tethered VR using a PC or console, or one of the more recent standalone VR platforms? Say you've decided a tethered solution is preferable, but which one? And just as important, why? These decisions cannot be taken at random. Just as you need to understand the properties of virtual reality and the requirements of the problem or task in order to say, yes, VR is the right solution, equally you need to understand the properties of the various hardware options and how they relate to the requirements of the problem in order to say, yes, this is the right bit of kit to use. As we talked about in the previous video, considering the alternative solutions against any given problem requires analysis. What worked for your last project won't necessarily work for the next one, unless the problem and the stakeholders are exactly the same, which is pretty unlikely. You need to do your homework to match the requirements of the problem to the properties of the solution. That said, there are a few pointers I can recommend to get your analysis started. The first pointer is to make sure you consider both pros and cons of each hardware option. Tethered VR may offer greater graphical fidelity and realism, plus typically much greater visual field of view, but the requirement of a pretty powerful PC ups the financial costs pretty significantly. No single hardware solution has only advantages or disadvantages. This seems pretty obvious when you consider the reasoning for these different platforms to exist in the first place, which is to provide a set of functions and qualities that the other platforms don't. Of course, these pros and cons are pretty meaningless unless contextualized by the problem, the availability of the alternatives, and the stakeholders. This brings us to the second pointer, which is to make sure you fully contextualize the pros and the cons. Are high-fidelity graphics actually necessary to solving your problem, or are they just a nice decoration? Do your stakeholders have a massive budget to deploy your solution, or are they very cash limited? Do they have any existing hardware, PCs, headsets, and so on that could affect how much they need to invest? These points have to be considered in context and balanced to properly identify the term we talked about in the last video, the added value of the solution. A good way of checking that you're doing contextual analysis correctly is to check that you're identifying across two important areas. These areas are opportunities and limitations. First, opportunities. Opportunities can be easy to confuse with benefits or positive features and qualities. But opportunities are a little more than simply what the hardware does well. An opportunity describes how one or more positive features of the hardware will help to solve the problem or complete the task. Let's stick with tethered VR for an example. Here, high visual fidelity is a clear benefit. If the task were architectural visualization, and the important requirement was extremely detailed and realistic visuals that would give the user an impression of an architectural space that was almost indiscernible from the real thing, now we have an opportunity. Here, one of the most significant benefits of the hardware corresponds perfectly with the primary requirement of the task. If, of course, the task changes, say to a learning exercise that teaches students about algebra, the benefit of this hardware option is still a benefit, but it's no longer an opportunity. Next, limitations. Now, limitations are essentially the reverse of opportunities. Rather than take the benefits or positive features of an option, instead they take the weaknesses, the risks, and the costs of that option, and then consider these points against the task, the alternatives, and the stakeholders. Sticking with the architectural visualization task, say another important requirement is portability. The solution needs to be easily transportable so it can be deployed at industry trade shows and various events. All of a sudden we have a problem with our previously favoured tethered VR option. Unlike a mobile or standalone platform, we have to drag around a desktop PC and its peripherals as well as the headset. This gives us a clear limitation. The last pointer that will hopefully help you to get started in analysing your approach is to outline the current major technical points that can be used to differentiate the different platforms and often individual VR hardware products. Here we'll take a brief look at visual displays and approaches to tracking. So let's start with visual displays. There are two levels of decision making here. What type of visual display to use, and then which specific device to use. The type of visual display differentiates between head-mounted displays, traditional flat-screen computer monitor type displays, and projection-based displays. It does occur to me that the type of visual display is a decision you've probably already made even now, and your decision is to use a head-mounted display. That's a fair call. As we saw earlier, the popular definition of virtual reality is something that uses a head-mounted display. If there's not a HMD, it's not VR, or some may say. Now, we've already discussed how this isn't an absolute truth, and virtual reality projects can most certainly use other visual displays. But when we consider the expectations of our stakeholders, we may find that they'll be disappointed if we don't use a HMD. This is another reason for why you need to understand your stakeholder. HMDs may be symbolic of modern VR and more supportive of immersion by fully obscuring the outside world. But they can be uncomfortable with extended use, they can be socially isolating, they can be awkward to set up, slow to attach and remove, and a bit embarrassing to use in public. Alternatively, a projection-based system allows multiple viewers to view a scene without needing multiple headsets, and it can offer a full 360-degree field of view. But installations can be very expensive, very difficult to transport, and not particularly interactive. Next, let's look at tracking. Broadly speaking, we may have up to three options: outside-in optical tracking, inside-out IMU tracking, and the more recent inside-out optical system. First, the outside-in optical tracking. This can offer very accurate tracking to 6 degrees of freedom, meaning it can track the rotation and the position of an object. The big advantage of this being that you can physically walk around a scene and explore the scene vertically, meaning you can look underneath things. Outside-in optical is less susceptible to drift, which means gradual decreases in accuracy over time. It's also less likely to be affected by metallic objects or magnetic fields. To balance out these benefits, outside-in optical is not particularly precise, meaning it's less sensitive to very small changes in position and rotation. It takes time and effort to set up, it's more of a pain to transport, and it suffers from what's called line-of-sight occlusion, meaning if an object accidentally gets between the sensor and the headset, then the tracking can break. Moving on to the next option, IMU-based inside-out tracking. IMU means inertia measurement unit. Examples can include accelerometers, gyroscopes, and magnetometers. IMUs can be built into a device, this could be a headset or a controller, to enable tracking. IMUs typically provide a high level of sensitivity. They support devices in being more portable and more lightweight, and there's no line-of-sight occlusion with this technology. These advantages are balanced out by high susceptibility to drift, meaning the accuracy changes over time, and they're also susceptible to magnetic interference. Plus, and this is quite limiting, tracking is often restricted to 3 degrees of freedom, meaning only the rotation of an object is tracked, not the change of its position. You'll probably have noticed that both visual display and tracking options share a similar property with the different headset platform options. In many cases, the advantages of one option are the reverse of the disadvantages of another option. This is a pretty reliable rule when making decisions about your approach to VR. But there can be exceptions when the technology starts to advance to the point that a single solution can offer more of the benefits of different alternatives with less of the disadvantages. One good example of this is inside-out optical tracking. Inside-out optical tracking most notably appeared commercially in the Oculus Rift S, which featured multiple cameras across the surface of the headset. Using these cameras in tandem with an image recognition framework, the Rift S was able to scan the physical environment to find features it could use as anchor points to enable tracking. This meant that the major advantages of outside-in tracking were retained. The Rift S gave 6 degrees of freedom tracking, it was not susceptible to drift or magnetic interference, and it did not suffer from line-of-sight occlusion and was a lot quicker and easier to set up than other alternatives. This brings us to an important theory of VR technology development that is often called the singularity. The singularity refers to the idea that as technology advances in various ways, eventually the variety of hardware options will begin to decrease as single devices become increasingly able to offer more advantages with less of the disadvantages that might encourage us to use different products for different purposes. The singularity theory expects this to extend beyond VR to all of extended reality, where somewhere down the line we will be able to experience all of the functionality and qualities of virtual reality, augmented reality, and mixed reality systems within a single device. Whether this will actually happen remains to be seen, but for now, there are still plenty of options, and you can't escape the need for fully understanding all of these options, and then applying this knowledge to select the best option for your specific purpose. So, to summarise, how we approach VR cannot be decided at random. In the same way that we need to analyse the problem or the task and the stakeholders and the available options in order to justify the use of VR in the first place, we equally have to go through the same process to make judgments on what platform and what hardware to use. Hopefully this video has given you some helpful pointers to get you started in your analysis, and moves you a step closer towards making informed decisions in your own projects. Of course, the general platform and hardware you select for your project is only the start of the considerations that you need to make. And in a later video we will move on to matters of user experience as we begin to build up a framework for not just what tools to use, but how to design and build a VR project that is ideally fit for purpose. Thanks for watching.